Hello. Today we'll be talking about the paper Composite Poisson Models for Goal Scoring, which was written by Professor Phil Everson, statistics professor at Swarthmore College, and his then student Paul Goldsmith-Pinkman, who's a professor at Yale right now, but who used to be a Swarthmore College student. So as an introduction, we will be talking about the English Premier League today, which is an elite soccer league, one of the most famous and popular soccer leagues in the world. There are 20 teams, most famously teams like Manchester United, which I'm a fan of. There's also Chelsea, Liverpool, Arsenal, Tottenham, and so on. And each team plays 38 games. So there are 380 games in total in a season. And 38 games in that, each team plays 2 games at home and at away against each and every other 19 other teams. So it adds up to 38 games. And in total, 380 games. And for a win, you get 3 points, one point for a draw, and no points for a loss. And at the end of the season, based on these points, you get ranked, right? If you end up with the same amount of points, you consider like head-to-head or goal scored or number of fouls or whatever, but that usually doesn't happen, so it's not really a problem. But this is like the basic structure and the rules that we want to know before we talk about the research here today. So basically, we want to quantify the strength of each team, right? And when we say strength, how likely you are to win, which is the same thing as how likely you are to score, right? Because you have to score to win in soccer. So we want to look at, or this paper dives into the framework to carry out inference for an additive Poisson model that could be applied to a variety of sports and data sets. And in this paper, we focus on soccer, but really it could be applied to hockey, lacrosse, or really any other sports that has really a few number of goals that's scored, right? So basketball would not be a good example or a field where we can apply this method. But a Poisson model, and especially the additivity of a Poisson random variable, was deemed appropriate for modeling the goal scoring ability of teams and players in soccer, and especially because not many goals are scored in soccer. So we want to estimate the team strength with Poisson distributions and differing home field advantages across teams. So we're going to talk about this later on in terms of the limitations of this model, but we are considering home field advantages, and because there are a lot of factors that goes into a team's scoring ability, and there are different types of goals that you can score, right? Whether it's because due to a player's individual brilliance, whether it's because of the team's tactics, right? Or it could also be, you could also score a goal because of the other team's mistakes, right? So we want to quantify and also classify different types of goals. And we also want a hierarchical framework with Poisson additivity and differing home field advantages, which we will talk about later. But this is the overall picture or big picture of the model that we're going to look at. And so the assumptions that we had is that when we estimate team strengths, we're going to have a parameter called offensive home advantage, which is the propensity to score more goals when at home than when on the road when playing comparable opponents, right? So soccer, home and away is a really big deal, especially for certain big teams. Like, for example, Liverpool is famous for their home stadium, Anfield, which is famous for their atmosphere and loud cheerings, right? And then there's defensive home advantage, right? So because when you're at home, we're assuming that your offense and defense gets better. And lastly, based on the overall framework, we're going to use a Gibbs sampler algorithm to estimate the parameters for the full model and adjustments for fitting simpler models, such as the common home advantage and no home advantage models. But we're going to dive into this. right away. So this is the level 1 model where we denote YH of 1I as the goal scored for the home team in game. So that's a random variable for the number of goals that the home team scores. And then we have another variable, Y of R sub I, which is the number of goals scored for the road team in game. So we're going to assume that each of the K teams, and because we're talking about a general model, we're going to say K, but for this case, when we talk about the English Premier League, the K would equal 20 because we have 20 games. And then we have an offensive parameter, delta O sub J, and defensive parameter, delta D sub J, which is just a pure offensive defensive ability. Sorry, those two parameters should be theta, but those are just how good you are as a team, regardless of home or away disadvantages, right? But you have delta O sub J and delta DJ, which are the home and away home field advantage parameters, right? And O is for offensive and D is for defensive, right? So here, as we noted, we have, as I've said earlier, for the home team, we add these 4 parameters. So at first, when I first looked at this, I was kind of confused as to why you would add, especially this delta road team parameter, right? Why are we adding the home team advantage for the road team when we want to estimate the number of goals that the home team scores? But that is because, first of all, this delta parameter, the larger it is, the worse it is for you. When it's a defensive parameter, the worse it is if it's larger, right? It means you're bound to concede more within a certain period, right? Because that's what like a Poisson parameter means. So as we add that to the home team's number of goals, that's basically an advantage for the home team because that home defense advantage, does not exist when this road team is on the road, right? So we add that to the home team. And as you can see, for the road team's number of goals, we don't have that type of advantage for them, or which is equivalently a disadvantage for the home team because home team is at home, right? So that's a kind of a confusing concept, but once you think about it, it kind of makes sense. But yeah, the road team's advantages that they would have at home, and because they're on road, they don't have those advantages. So we add that to the home team. So it's an advantage for the home team, but a disadvantage for the road team. Which, if you think about it, makes sense. And it was I thought this was a very clever design by Professor Iverson and Paul. Right. So then this model allows teams to vary in their ability to both produce and prevent goals, right? And it also requires that teams play at least as well at home. So the delta parameters must be non-negative, right? So that we don't end up with a negative parameter for the Poisson random variables. And we maintain this additive property of the Poisson distribution and avoid possibly fitting a negative mean. So for example, and this is, I guess, an additional explanation. So if Team J has a stronger defense, right, and tends to allow lesser goals, then the parameters such as the delta D and the theta D should be small. So the rate is small, right? So when added to the road team's defensive parameters, right, if those defensive parameters are small, it doesn't help the home team's offense, right? And if they're larger, they do help the home team because it means that the defense leaks a lot of goals and it would lead to the home team to score more, right? And then, yeah, they're added because at home or when they're on the road, they're missing those kind of advantages. So it works against the road team, but towards the home team. So it was a very clever design to think about these added Poisson properties. And when it comes to these home advantages, I thought it really applied well to these models. So if you think about the neutral field means, then we do not add that, or we add it to both sides, right? So the delta D parameter is added to the rate parameter y sub ri, and for the same reason, the delta D ri is added for yh, because now both teams are missing that home team advantage that they would have. So we assume that both home and road team, in this case, it's not home or road, but neither of them exhibit or enjoy that home team advantage or that they have, whether it's defensive or offensive. So we add the other team's delta parameter to a certain team's goal number source, right? So we're adding that other team's home advantage, which is really funny if you think about it. It's counterintuitive when you first think about it. Like, why would you add the other team's parameter? But because it's that team's home advantage, it makes sense. So based on these models, what do we do? So we assume a common conjugate gamma distribution for the offensive and defensive parameters, denoted as theta, and common gamma distribution for the home advantage theta. So this is how it looks, right? With alpha and beta values, that looks like this. So that these theta and deltas are modeled to have a mean mu and a variance of mu squared alpha, right? That's what you get if we compute this. So that mu defines a typical value for the K teams, and increasing alpha makes this distribution more concentrated about the mu. And we can partition these goals. So like we said before, because of the additive property, we can conveniently split up the number of goals that's scored by the home team based on these categorical features of these different goals. And obviously, these aren't the only factors when it comes to goal scoring, right? There's a lot more, like mistakes, I don't know, even like weather. And other thing that you can think about is like there are certain teams that are good against really. It's like there are times where a weak team, the team that's not supposed to win, like supposed to, as in like statistically, like speaking, like this team shouldn't be winning a lot of the games if they play a certain team, right? Because they rank lower, they have lesser players. But there are scenarios in soccer where like these upsets happen, right? I guess it's a thing. I guess it would also be a thing in NBA, but more so in soccer, like because in England especially, there's like culture, there are different rivalries, right? So there are a lot more factors that come into. So that's a limitation of this model. But here we have like 4 basic or very overarching categories. So we partition these goals like this. So these equivalences follow from the additivity of the Poisson distribution. And because we designed it like this, we can assume that the model classifies goals that, due to a strong offense, due to the road team's poor defense, or due to the home advantage, and so on, right? And the simplicity of these distributions, the way we partitioned this, helps us to learn that these values are hypothetical, right? And these land variables, we can easily estimate them, right? The deltas and the thetas using the standard Poisson inference techniques, right? So we can easily, for team J, we can come up with the delta, the offensive parameter, and the average of the offensive totals for team J in a certain number of games, right? Because they will score a certain number of games, right? And then we can also get to know about the thetas and deltas and deltas and thetas and make the inferences about the unknown partition counts, right? And this is all due to like the Poisson additivity, right? Which is conditional on the total count, and the distribution of the partial counts are binomial, right? Because we'll be counting these number of goals, right? When we actually look at the data. So that it helps we also take advantage of that and come up with these conditional partitions where we take the ratio of the number of goals, right, for the number of offensive goals over all the other parameters, and we use the same logic for the other goals as well, right? And it's a little more simpler for the road goals, right? And based on these assumptions and models, we get an outline of the algorithm, right? So we can determine the starting values, initial values for these initial parameters, right? Just by looking at the data and the gains, and then using these data and like there's so-called strengths and home advantages, we can generate these random partitions for the variables and then get the actual total gathered or the combined random variable, right? And use them to generate the estimates for the delta and the theta offensive parameters, and generate the means and alpha and the mu pairs for the joint posterior densities given the deltas and thetas using rejection sampling. And then we can, as the last step, use the conditional posterior distribution given the actual parameters, which can be easily done with a Gibbs sampler, right? As we've been doing in class, we yield the draws from the joint posterior distribution of the unknown parameters, given the goal totals, right? We'd be actually looking at the data, and we would come up with that. And then we have a little more detailed algorithm, and there's also like a good chunk of calculations that isn't included in the presentation, but I think this part of the detailed algorithm can be I can answer questions if you inquire of it, and I can also send you the paper. But these are the detailed steps. But basically, this is the result that we get, where for each team, so this is like the lower bound, this whole on the left side, higher bound is on the right side, and it's a confidence interval, and the red dots are the points where they actually end up with. So about 13 teams out of the 20 teams actually ended up with points within that confidence interval, which is pretty impressive if you can guess or come up with a 90% interval for where the team would end up with the as in terms of the number of points. So that was pretty cool. And this is the result that they had for the paper. And this is, I think, where a lot of problems came up, because it's not like I don't disagree with the numbers, but their data didn't seem to match with the actual data, because in the paper they said they looked at 2006 data, and here in terms of the results, they're saying this team called, for example, Portsmouth ended third, but when I looked it up and did some research, Portsmouth never ended third in their history of the club. So there were some issues with their data acquirement, or however they worked with the data. And I actually got the source code just today as I'm presenting, so I couldn't do the error checking or run the code myself to actually see how they came up with these results. But that's something that I wish to do even after this class ends today. So if you guys are interested in what kind of results did I get, because I'm a big soccer fan, especially a United fan, so I want to see how this works. So I want to check correct this graph and potentially use it for like future seasons as well. So if you're also interested, please let me know and reach out to me. But thank you for listening. Thank you for tuning in. That's it for the presentation.